Alrighty, let us get started. So the plan for today is to continue our discussion with thermodynamics, but moving on from the previous topic, which was heat conduction, and to start talking about the next method of heat transfer, the last one we're going to talk about, which is the transfer of heat by radiation. So before we get into the math, the actual calculations, what equations are there and things like that, let's make sure we understand the conceptual view of how radiation works. First of all, the term radiation, of course, can be used for several different physical phenomena. Of course, usually when you hear of radiation, you think of nuclear things, radioactivity, things like that. And indeed, as it pertains to radioactivity and radiation in that sense, the kind of nuclear radiation, one form of that type of radiation is the release of energy, light. But of course, with nuclear radiation, we have other forms, other particles, other things that are radiated from a decaying nucleus, let's say, which may not be light. So you may have things like alpha particles, which are helium nuclei being shot out of a nucleus as it disintegrates, or electrons or positrons, antimatter, different things can be a part of the nuclear decay radiation. The radiation we're discussing here, however, is more along the lines of light escaping from an atom, not necessarily from its nucleus, but rather from its electrons. And so, just to have a nice little visual thing, remember what I'm about to show and kind of give rise to a story is not actually how it is in reality. This is nothing more than a visual attempt at understanding, to try to have some perception which makes sense to our minds on what's happening. But of course, the reality of the situation is not exactly as this. And so what we're going to do is think about an atom. Of course, an atom has its nucleus, and then there's several electrons which buzz around, circulating around the nucleus, right? And of course, if we know anything about chemistry, which of course I have to say as a physicist, chemistry is nothing more than the focus of one part of physics. Physics is the fundamental science which describes all phenomena, and chemistry just kind of specializes in one small area. And so when I say chemistry shows us this, what I really mean is physics tells us how it works. Chemistry studies it as a specialty. And usually you see this stuff in a chemistry class. And what chemistry says is there are certain orbitals, so certain regions where the electrons are allowed to orbit around the nucleus, and they're quantized, which is a little bit of how quantum mechanics arises. The fact that an electron in this orbit, let's say this outer orbit here, versus an electron in an inner orbit here, there's some energy gap here, some amount of energy, and I'll label it as gamma, that if I can give the electron in the inner orbit this excess energy, it'll push it out to the outer orbit, and it'll be happily orbiting around at this far out region until such time as it gets tired of doing that. Of course, we think about the electrons as being lazy. They don't like to be excited. They don't want to have excess energy. They want to be at the lowest energy state they could possibly be. So eventually, the electron will give away that excess energy and fall back down to the lowest orbit it can possibly fit in. And of course, when you study chemistry, you learn how many electrons are allowed in each level, and their spins make a difference, and all sorts of physical reasons why things work the way they are. However, what's important for us is the fact that an electron is allowed to move from one energy level, one orbital, to another by means of gaining energy or releasing the energy. And when I say energy, energy is light. And one form of light, one form of energy is heat. Heat is nothing more, or can be thought of as light of a certain energy level, of a certain frequency, which visually we can't see because the energy is too low. We need a higher energy light to be able to see it visually, but not too high, or else then it becomes invisible again. And so infrared seems to be the place where most heat energy arises. So there's a certain energy range called the infrared range of the spectrum, where the light which would be released is energy in the form of heat. And so if you have an atom and you have some of its orbitals, some of its energy levels are separated by a certain amount of energy, and that energy happens to be in this infrared range, then what you'll have is the transfer of heat from one object to another by means of radiation. Literally, the electron in the outer orbit shoots off a photon, shoots off light. And in doing so, the electron falls down to the ground state, or the lowest energy state it can. And then something else can absorb that light that was sent off. Maybe there's another atom over here which has his own electrons orbiting around. And if that light is absorbed by this electron, he can move up to a higher energy state, and so on. And basically, this energy is propagated to various atoms like this. So that's what radiation is in this context. It's nothing more than the energy released by the electrons moving from one energy state to another. The energy state difference gives rise to the energy of the photon. How energetic is it? What's its frequency? What's its color? And if it's in a certain range, then we call it heat. If it's in another range, we call it radio. Another range, it's microwave. Something else, it's gamma waves. Visual. Different ranges of the spectrum, different amounts of energy are just named different things. And so that's what radiation is as a physical concept, as a visual thing, what's going on. Now, what we're going to try to do is, of course, analyze systems and figure out how much heat may be radiated out by an object because of its temperature. Because obviously, that's what's allowing these electrons to get excited in the first place. In order to excite the electrons, they must be fed excess energy. How do we feed it excess energy? Maybe we put a fire under the pan, or we heat the piece of metal up. We give it this excess energy in some way. We shine light on it, or a laser beam or something. Or we rub it with a frictiony towel or something, and it heats up the object. Those electrons now have the excess energy. Eventually, they fall back down to lower energy, sending off their own light waves. That's the radiation. And I want to know how much radiation is sent off per second because of how hot the object is. And so what we have is, just like before with conduction, a nice little equation for the heat transfer rate, how much energy will flow per second. given by an equation which is sigma epsilon a t to the fourth. Now, what are all these variables? Sigma is called the Stefan Boltzmann constant. It's just a number. And the number happens to be, I believe it's 5.67 times 10 to the minus 8, if I remember correctly. Yeah, and then the units would be watts per meter squared Kelvin to the fourth. Weird units. The number is what's important, though. 5.67 times 10 to the minus 8. Pretty easy to remember, 5, 6, 7, 8, sitting there. But that's the number. So that's sigma. Epsilon. Epsilon is called the emissivity. Vidi. And this basically is about the material. How easily does this material transfer the energy? Just like before with heat conduction, certain materials, as they heat up, will allow their electrons to change their orbitals easier than other materials. And the emissivity basically gives you some kind of a feeling for how much of its energy will be released. And usually this is somewhere between 0 and 1. Okay, 1 is a perfect radiator. That is to say, all the energy that's fed to it initially will eventually radiate out perfectly. Of course, usually real world materials are not perfect. And so maybe they only radiate 75% efficient or 80%. That would be 0.8. But if I say in a problem, this is a perfect radiator, what that means is the emissivity, this epsilon variable, is 100%. Usually it's between 0 and, well, it has to be between 0 and 1. All right, the next, A. This is, of course, the area, but this time it's the surface area. So when we're talking about an object that can radiate energy, let's say we're talking about a star. You have the sun, it's undergoing nuclear fusion, that's heating up the sun. All that excess heat is being poured into the electrons of the hydrogen gas, which is what makes up the sun. And that makes it glow because it's very hot. The electrons in the hydrogen gas are at an extremely high energy level. As they cool, as they're near the surface, they release this energy as light being sent to the earth. Now, obviously, if what we're looking for is how much energy is sent off per second, how much is radiated, notice that only the surface of the object matters. In order for this light to leave the object, it has to be at the surface. You know, if I'm talking about a sphere like a sun, so here's my sun. Well, the only way light can escape is if the light is on the surface leaving. Light that's in the center of the sun is in the center. As soon as it's sent off, it hits another piece of hydrogen right next to it and it gets absorbed again. So the only light or heat which can radiate must be at the surface. And so what's important in this calculation is not the mass of the object or how big it is or its volume, but rather its surface area. How big of a surface do you have? The thickness doesn't matter. The surface is what matters. And so it's the surface area. Now, one thing to note for surface area, one of the big ones we get is the surface area of a sphere. If I'm talking about a nice metal sphere that I'm going to heat up with a torch, and it's going to eventually start to glow red and radiate this energy, then I need to know what's the surface area of a sphere, or a star. What's the surface area of a sphere? And the surface area of a sphere is given by this equation. In case you don't know it, it's 4 pi r squared. Okay. Let's say you want the surface area of a cube. What am I doing? Cube. I have a metal box, and a metal box I'm going to heat up, and that's going to radiate energy. Well, what's the surface area of a metal box? Well, if you think about what a cube looks like, I'm going to try to draw something that kind of looks like it, but I'm not perfect. What do you have? All I care about, I don't want the volume of a cube, which would be length times width times height. What I want is a surface area. And so what I do is I look at what's the area of this face I can see, and that's length times width. And then what's the area of this face? Well, maybe that's, let's say width times height. And then what's this face up here? Maybe that's length times height. So you have 6 faces of a sphere, right? Front, back, left, right, top, down. 6 faces, each face is length times width, basically, the area of a face. If it's a cube, a perfect cube, then it's 6 times length times width. Okay. If it's not a perfect cube, but it's like a box, a rectangular box, then you have to add each face individually. You'll have length times width for one face, width times height for another one, height times length for another one, and you add all 6 faces together. Each one, you find the area of the face, and you add all 6 together. Here, since all 6 are the same, being a cube, we do length times width for one of the faces and multiply it by 6. And then, of course, you can do the same for other shapes. If you had a pyramid or a cone, you could do whatever the surface area of those shapes are. All I care about are these 2. When I give you problems in this class, in radiation, I'm either going to give you a sphere, so a sun or a metal ball or something like that, or I'll give you a cube, a box. So these are the equations to calculate the surface area. So it's important to know. And then, of course, the last piece, temperature. This is temperature. The hotter the object, the more energy it can radiate, because you've excited it. You've given it extra energy to begin with. It doesn't like having extra energy, so it's going to try to radiate it away. So the more you heat it up, the more excess energy you've given it, the more energy it has to give away. And what's unique about radiation, yeah, question. I'm sorry? Okay, maybe it was an accident. What's unique about this particular equation, this radiation, is the fact that it's t to the 4th. A 4th power in an equation. You don't see that very often. And so this is just, for whatever reason, it sticks out in your mind. When you talk about radiation, it's t to the 4th, a 4th power law. And so if you ever see an equation with temperature to the 4th power, you know it has something to do with radiation. Another thing to know is that since this equation is not delta T, remember that's not a delta, that's an A, in case it looks like a delta. This isn't delta T like conduction or calorimetry. We talked about the change in temperature or the difference in temperature. With those, we use the fact that Celsius and Kelvin was the same thing. Here, we don't have that luxury. Now what we have is an equation which requires the absolute temperature, not the difference in temperature. And thus, we have to use Kelvin. We must use Kelvin, not Celsius. If we try to use Celsius, we'll get a bad answer. And of course, same goes with Fahrenheit. So here we have an example where we do have to convert all of our temperatures to Kelvin scale if they're not already in the Kelvin scale. We've been lucky with the previous topics we've been doing, where we can get away with the fact that a delta T of Kelvin is the same as delta T in degrees Celsius, but now not anymore. But there you go. With this equation, I can say you have a star of a certain size. Its emissivity is 90%, and the star is at 10,000 Kelvin. Question is, what's the heat transfer rate through radiation? Another thing I'll say is a lot of times, instead of calling it heat transfer rate, we'll call it the power. So with conduction, we call it heat transfer rate. But really, when you think about physics and you think about the units of joules, which is energy per second, so Q over T, heat per time, is joules per second. Joules per second in physics is what power is. Power is defined as the amount of energy transferred per second. So when you talk about a machine, how much work do you do per second? Work is the same as energy. Or what's the power of that motor? Well, the power relates to how much energy, how much work this motor is going to do to turn your tires, for instance. So a lot of times when we talk about radiation, what the question may ask is what power is radiated by the star, rather than what's the heat transfer rate. Okay. Either way, what we mean is Q over T. So if you hear the word power, just know it's the same as Q over T. But there we go. That's the theory. The conceptual view, how is this radiation even occurring? Well, it's just the electrons in the atom being excited to higher energy levels, eventually wanting to settle down, sending off that excess energy in the form of light. That light is of a certain energy, which makes it heat instead of visual or visible light, or microwave light or radio waves or something. So let's try an example. How do we use this equation? You have a metal sphere whose radius is 50 centimeters. If the sphere acts as a perfect radiator, what would be the power radiated if the sphere was at, let's say, 500 degrees Celsius? So that's a nice basic radiation problem. I have an object of a certain shape and a certain size. I know its properties. It's a perfect radiator, whereas something else may have been a 65% radiator or something. And I know its temperature. How hot did you make this sphere? Given this information, I'd like to know how much energy is transferred per second. What's the power radiated by this sphere? Well, all we have to do is use the equation. Q over T, which is called the power, is sigma epsilon A t to the fourth. Well, sigma, that's just a constant. That happens to be 5.67 times 10 to the minus 8. Just a number. Epsilon, the emissivity. In this question, we're told this is a perfect radiator, so the emissivity is 1. Then I need the surface area. Well, in order to calculate the surface area, I need to know what shape is my object. I'm told I have a sphere. And so I know that the area of a sphere, surface area, is given by 4 pi r squared. So for this sphere, it's 4 times pi times the radius of the sphere, which is 50 centimeters. However, again, centimeters is bad units. So we have to convert centimeters to meters. And so it becomes 0.5 squared. So I get out my calculator. I say 4 times pi times 0.5 squared, and I get a surface area of 3.14 pi. The 0.5 squared and the 4 happen to cancel out. But there it is. Area of this sphere is 3.14, so I plug it in. And then t to the fourth. Well, I'm told the temperature of the sphere is 500 degrees Celsius, but Celsius is bad units now. So now I have to convert temperature. 500 Celsius. How do I make it Kelvin? Well, remember the conversion. The temperature in Kelvin is whatever it is in Celsius plus 273. So I just add 273 to this number, and I get 773 Kelvin as a temperature. So 773, and this is raised to the fourth power. And now I have my equation. Sigma, that was just a constant. Epsilon, that's given in the problem as the emissivity. This one is called a perfect radiator, which means emissivity is 100%. 100% means 1. Then I have the surface area. This is a sphere. Surface area of a sphere is 4 pi r squared. I take the radius, convert it to meters, calculate the area. I get a number. Temperature. Temperature is given in Celsius. That's bad. I have to convert it to Kelvin. So I add 273 to the number. And now that's the temperature I use in my equation. From here, I just plug everything in my calculator. So I have 773 to the fourth power times pi times 5.67 raised to the minus 8. And I get a power of 63599.1 watts. Now remember, joules per second, which is the units of Q over T, is the same, is defined to be the same as capital W or watts. Okay, usually you see watts when you do circuits in general physics. And so when you get to electricity and magnetism stuff and you start doing circuits, you're going to see this unit of watts pop out. You also see it in first semester physics when you talk about work and energy, you talk about power sometimes. But here we're seeing it. So you can either use units joules per second, or you can use the units watts. Doesn't matter, they mean the same thing. But there we go. That's how much power is radiated by this particular sphere. Are there any questions about this example?
Can you go over the steps again about how you got the answer? Because I put it in my calculator and it was like error.
You got an error, Okay, well, when I do this in my calculator, I'll tell you exactly what I do. First thing I do, this fourth power thing is the weird thing. So I'll first do 773, and then there's that little caret, little up arrow thing, to the fourth power. And then I'll push enter. And this will raise 773 to the fourth power for me. So now I have a number in my calculator, which is that. Then I say, whatever that number is, I multiply it by the 3.14. And then I push enter, and I get a number for that. Then I would multiply by the emissivity, but that's just 1, so I don't have to multiply by 1. So I take whatever this number is that's in my calculator, and I do parentheses, 5.67, and then I have a button EE, like it looks like this, which means that EE symbol means times 10 to the whatever power I'm about to write. So I would do 5.67, that EE button, minus 8. And then I'd push enter. And that's what gave me this number. So the first thing I will note is what I see a lot of times when students aren't used to their calculators, or they're not very comfortable with it, when they write this, you try to actually write out times 10 raised to the minus 8 power. I see people do that a lot. That's fine, it works, but you don't have to. Scientific calculators have this little button, which is 2 capital E's, like this. And so what I do, let's say I want to write 3 times 10 to the 6th. All I have to do in my calculator is I do 3, then I push the EE button, 6. And these two things are the same. Okay, so when I did this in my calculator, all I did physically was I did this step first, 773, and then a little caret symbol 4, and that means 773 to the fourth power. Then I push enter. I now have the answer on my calculator. Then I push times, so it takes that answer, multiplies it by 3.14. Then I get an answer, and then I say times, and then I write this 5.67 EE minus 8, and I get an answer. And that should give you this 63. So if you try it that way, do you get the answer now?
Yes, sir. Thank you.
Okay, good. And another thing to look out for, just in general, is don't be afraid to use parentheses all over the place. Sometimes you may think you're doing something on your calculator, but your calculator is kind of unsure of the order of how to do things. So the more parentheses you use, the more likely it is you're going to force the calculator to do what you want. For instance, if you're not careful, then what may happen, for instance, when you do this, this 5.67 thing, you may do 5.67 times 10 raised to the minus 8. Well, this it may try to do, and then raise to the minus, and then you have just this 8 sitting out here by itself. Calculators are really stupid. So what you have to do is, when in doubt, plug in parentheses to show this whole number I'm doing raised to the fourth power. Or I want to multiply all of this by this next thing. Okay, I see a lot of times students don't use parentheses anywhere. And sometimes it works, you know, it's fine. If the order of operations is okay, no problem. But I use parentheses even when I don't have to, just to ensure that the calculator does everything in the correct order that I want it to. And this is how I always do it. I don't ever plug everything in my calculator in all at once. What I do is exactly as I said here. I take the first thing and I get an answer for it. Then I multiply by the next thing and I get an answer. Then I multiply by the next thing. And this helps limit small errors that might occur either in what you're typing, or whether your calculator knows, are you multiplying or dividing this thing, where are the fractions, all sorts of stuff. So just another tip when using your calculator is you don't have to try to stick everything all in one line all at the same time. Just do one little piece at a time. Multiply them up one at a time, get an answer each time, and multiply by the next thing. And then you get your final answer at the end. At least that's how I do it. Any other questions on this particular example? Now, of course, this can be modified. Firstly, just like with conduction, yeah, we found the power radiated, but maybe I want to know if you wait, if this is the sun and it's radiating its energy out, and you found out how much energy it radiates per second, what's the power of the sun? Well, another thing you could say is in 1 year, how much energy does the sun radiate? Or maybe in 1 day. In 1 day, how much energy, the total amount of energy does the sun radiate? Well, all you have to do is remember that originally Q over T is sitting here, and that means power. But that's the same as how much energy divided by the amount of time we wait. So I could always just move the T over here and have some new equation that's Q equals sigma epsilon A T to the fourth times T, little t, time. So I'd still have all these numbers just like before, only now I know this is 1 day. So I convert that to seconds, however many seconds there are in a day. And that'll give me the total amount of energy radiated in 1 day, or 1 year, or 5 seconds, or whatever it is you want. So just know that although this main equation is an equation for power, you can manipulate it just like all your equations to solve for something else. So maybe I ask you, what's the power radiated by the sun and how much energy will it radiate in 1 day? Well, calculate the power. Once you know that, that's Q over T. Move the T over to solve for Q. So that's the first modification that can be done. Another modification goes like this. Well, this calculation works, let's say for a star out in outer space. But what if instead what you have is a hot object in a place that is already at a background temperature? So in other words, if you remember heat conduction, I said if the difference between the outside temperature and the inside temperature is really big, then that heat really wants to pass through quickly. But if the difference in temperature is very small, if they're really close to the same temperature, then the energy doesn't go through that quick. The heat transfer rate slows down. Same thing is going to happen with radiation. If what you have is a very hot object and you put it in a cold environment, that object's trying to release its heat as fast as possible to its surroundings. However, if you have a hot object, but the room it's in is also hot, then the heat doesn't have to radiate that strongly. It's not trying to get rid of its energy because the surrounding area is already at a high energy. There's no deficit there. So how do we worry about the fact that sometimes you may have an object radiating in an environment that's not space? Maybe you put it in a refrigerator. Maybe it's in an ice chest. Maybe it's sitting in your room, whatever it is. The background temperature isn't 0. It's some other number. Well, the modification goes like this. The power radiated by an object at a certain temperature T in an environment, which is at some other temperature, is sigma epsilon A. Now here's where things change. We're going to do a delta T here. But before I give you the answer, I have two options for how this can go. What we have is the temperature of the object and a temperature of the environment, right? So say we have a metal sphere that we heated up, and I can either put it in a refrigerator and let it radiate inside the refrigerator, which is cold, or I could have it in a barbecue pit that's also really hot. So the environment matters here. So the question is, if both of these temperatures are going to matter, should I do temperature of the object minus temperature of the environment to the fourth power? Or instead, should it be temperature of the object to the fourth power minus temperature of the environment to the fourth power. Both of these take into account the energy of the object and its environment. Both of them have a fourth power, which is what this equation needs. However, are we doing the difference in temperatures first and then taking the fourth power of that thing? Or are we taking the difference in the fourth powers? Well, here's the spoiler. This is not what we do. Unfortunately, we have to do it this way. And I say unfortunately because if it was the first way, then what it would be delta T to the fourth power. And you see, delta T is sitting there. Now I could use Celsius again. But that's not how we do it. You can't do it that way. Instead, it's T to the fourth minus T to the fourth, not delta T raised to the fourth power. So again, even though it looks kind of like a difference in temperatures, we still need Kelvin. You can't use Celsius here. But that's the way it is. You now know that's the rule, so follow the rule. The equation is temperature of the object to the fourth power minus temperature of the environment to the fourth power. So that's our two equations. The power radiated by an object at a certain temperature. And then if we put this object not in space, but in some other environment, which is at its own temperature, then you have to take that into account with this equation. So the first part is the same either way. The difference comes in with the temperatures. If you're in an environment that has its own temperature, you use this second equation. If not, if we're talking about a star or I don't tell you about the environment, then you just do the first way, like we did in this example before. So are there any questions about that? Okay, so just don't let it confuse you because it's very tempting to see that delta T looking piece and say, delta T, I don't have to convert anymore. You still have to convert because it's not really delta T. It's the difference of the fourth powers, and that's not the same thing. But that's it. That's all the theory for radiation. You're either going to be getting the first equation or the second one. And the difference is purely, does the question tell me about the temperature of the environment, the background temperature? If it doesn't tell me, then I use the original equation. If it does tell me, then I use this new updated version. Either way, what you're solving for usually is the power radiated by the object. Of course, I can always say, if I want the power to be 50,000 watts, what should the temperature be? Well, now I'm just solving for T instead of Q over T. Okay, just like before, I know I shouldn't have to mention it every time, but anytime you're given an equation, any one of those variables can be solved for. So just be prepared. I don't have to ask you for power. I could ask you for temperature or what's the radius of the sphere? That's the area. At least you use the area to get the radius and so forth. So all that's left, of course, is to just work a bunch of example problems with this stuff. The theory is finished. There's no new equation, no new concept involved. As long as you have a visualization of what radiation is all about, and you can work with this equation, then you're going to be golden. So I think I'll go ahead and leave it there for the day. No need in moving forward. Next class, we will do the example, more examples, obviously. That's the plan for Thursday. Work a bunch of examples. And from there, we should probably be good with it because there's not a lot of nuance to this radiation stuff. If so, then the future is Tuesday of next week. We'll have our first test review. And then Thursday, we'll have our first test. And of course, that's going to be on all the thermodynamics stuff. On a test review day, I'll talk more about it. But just so you see what's coming up next Thursday, it looks like we'll probably have our first test. And again, if you did not have me for first semester physics, and so you don't know how my tests work online, the way it'll be is just like the homework assignments are. I'll post it in the morning, you download it, you work it out on your paper, submit it back to Canvas by 11:59 that night. You don't have to do it continuously. It's not timed on the website. You do it just like you do homework, and then submit it back by the deadline. But we'll discuss it more when we get to test review time. So other than that, unless you have any questions for me today, we will do some examples on Thursday, and I'll let you go. Enjoy the rest of your day.
Hey, I have a question. Oh, you can go ahead.
I think they were just saying have a good day. I appreciate it. Go ahead.
Oh, okay. So I was working the other problem out and I got a different answer. It was like, it was still 635, but it was 88 instead of 99. So I didn't know if I had did it wrong still.
Did you write, did you put in pi itself or did you do 3.14?
3.14, you want me to put it in pi?
No. Oh, that's exactly what it is. Yeah. I think I did pi on my calculator instead of 3.14. That's close enough. If this were a test, I would know it's the same answer. The difference is I only wrote 3.14, but really the answer is all of pi, which is 3.141592653, all that. And so because I plugged in pi instead of 3.14, the rounding was a little bit different here. So yeah, you had the right answer.
Okay, thank you. That was all.
Good, perfect. Any other questions? All righty. Well, I wish you all a good rest of your day, and I'll talk with y'all on Thursday.
Thank you.
All righty.